渠道上，互动渠道上。
Okay, I start. I met with the TAs this morning, and they told me that we would be done grading by Wednesday, so I will be, I believe if all goes as planned, we'll hand back the homework in class on Wednesday. We discussed generally how people had done, and there were a number of issues, and I just want to point out some of them, and then if you have questions after you get your papers back, then you can talk with me or talk with the TAs first and grade the homeworks. So there are a number of things that they noticed, and maybe you can just list them somewhere here. Okay, so just some general things. Maybe I'll write them up and post an announcement. The one thing is just you should understand the solution you submit. That seems kind of silly, but that means that if you, for some reason, looked up the answer, looked it up online, and did just found exactly the match for the problem, and then you submitted something that was just a slightly modified version of that, that's not good. And it's often pretty noticeable because you can sort of figure out where all these results originated. So if you are looking stuff up, you should understand what you have found, and you should take some time to do that, and use that time also to figure out how to formulate your solution. All right. Another thing is that in many cases, see the code. Can help? Okay, so if you explain an algorithm, sometimes it's harder to do it in words, in regular prose, than it is to just write a pseudocode outline of the algorithm. That way, you save some time. It's easier to grade it, easier for you to understand. It helps me when I write algorithms to write some kind of pseudocode so that at least I understand what is involved. Right? Another thing is that correctness proofs are important, meaning that if you present an algorithm and you give me a pseudocode, it's not enough to repeat what the pseudocode does. You have to articulate what the reasons are that implies your algorithm is correct. So you should state the main points and indicate how your algorithm addresses them. In particular, there was one problem that was, I forget, it was one that basically amounted to telling whether a graph could be split into two parts. Good guys and bad guys or something like that. And that would have been a case where pseudocode would have helped and the correctness proof would be necessary. Curiously, that problem is solved in Kleinberg and Target. So there's a solved problems section at the end of every chapter, and there is one at the end of one chapter, I won't tell you which, there's a description of how you can test by part vectors, and that's a good illustration of how you could present a solution. All right, so that was one thing. All right, the other thing is that if you have questions about grading, my TAs encouraged me to tell you to go to their office hours and ask them what you did wrong, if you did something wrong. And as far as writing, less is more. Okay? 3 exclamations, maybe you have to put 10. Okay, so you write a lot, it's not good. It's usually a bad sign. If you're finding like you fill a page full of text, that's usually very bad. If you're going to write, it's better to write less and make every word count, because that gets your message across easier and more quickly. It makes it easier for the grade. It's good practice for the future when you have to write memos or when you have to write papers. Always better to be concise. All right. So that was my summary of what we found, or what the TAs found, that they were great. If you have questions about this, we can talk about it after you get back to your home. Right. So let me step back here and talk about something we were doing the other day. And I'm not going to add a lot more to what I did, but I just want to review a few things before. Here's the problem. Okay, so I've got network, and in this case, the network is a flow network in which I have the usual capacity. So this number here is 10, the capacity, and I want to find flows in this network. And this is a special kind of flow problem. In which I have certain nodes that are suppliers of something, and other nodes that are consumers of that thing, and I want to ship whatever that thing is from the suppliers to the consumers, the demand nodes, through the network. And some nodes are neither consumers nor suppliers, and so they just kind of serve as intermediate destinations, the transshipment. All right. Okay. So here's an example of what we did the other day. So there's a flow taken straight from Kleinberg Target. There's a flow, and in this case, the flow satisfies all the demands. Okay, so let's see. So I've got so we have a demand for every node B, and if this is bigger than 0, this is consumer, and if this is less than 0, this is a supplier, and if it's equal to 0, this is a transshipment node, meaning that it only lets things through. Okay, so the point is that if you have a node like this, here's B, with some edges coming in, some edges coming out, the amount of flow that comes in minus the amount of flow that goes out should equal the demand at that node. And that's the second constraint. And the first constraint is just the usual capacity constraint. All right, so if this is a feasibility problem, it's not an optimization problem. The problem is there a flow that meets the supplies of the demand constraint? All right, so this flow, if it exists, is called a circulation. That's what this thing is, right? So a circulation is a flow that satisfies these constraints, and it may or may not exist. So the question is, does it exist? And what I argued last time is that it's very easy to convert this into a flow problem, into a maximum flow problem, which is this. Okay, so I just add a source and a sink. The source is connected to all the supply nodes. All the demand nodes are connected to the sink. And there exists and I should also say that the capacity of the edges out of the source equals the negative of the demand value for the endpoint of that edge, and the capacity of the edges into the sink equals the demand at the origin of that edge. All right, so the claim, and it's not, I guess, really hard to see, is that there exists a circulation if and only if there is a flow in this network where all the edges out of the source are saturated and all the edges into the sink are saturated. And of course, I'm assuming that the total supply equals the total demand. In this case, the demand is 11, the supply is 11. So in this case, the answer is yes. So the problem is I take a circulation problem, does there exist a circulation, and convert it into a maximum flow problem. And once I've solved the maximum flow problem, I just ask, are all the edges out of the source and into the sink saturated? If so, I'm done. If not, then there is no circulation. Okay, so we have a reduction. All right, so that was the first one. Any questions about this one? Because it's circulation. So I'm taking, so here, see if I get it right. So my original problem is circulation, and I'm converting it into max flow. That's a transformation. And I have a transformation from circulation to max flow, which is shown there. And then from the max flow answer, I can get back an answer to the original problem by just looking at the edges of the source and into the sink. That was the first one. The second problem is a little bit, it's just an extension on this. So in the second problem, what I will require, in addition to meeting supplies and demands and also the capacity constraint, I'll also require that the flow on each edge be at least some amount. Okay, so if I all right, so here I have it. UV and okay, so I have each edge now has two values. One is the capacity, which is the larger number, and the other one is the lower value. So the requirement is that the flow be less than or equal to the capacity and bigger than or equal to the lower bound. right? And I still have supplies and demand, so each of these nodes has a value d of u and a value d of u. Right, so this is circulation. The problem is to determine if there's a circulation that meets not just these demands, but also the lower bounds. Is it circulation with lower bounds? Yes or no? And what I showed the other day, or at least sketched, was that you can convert this into a problem in which that looks like this, in which I don't have any lower bounds. And the trick is, in fact, quite simple, but it does require some thought. So what we do is we replace each edge like this by, well, the same edge, but the capacities are changed. So in this case, the capacity is going to be the C of E minus the lower bound. It's going to be 7. Okay, so in this case, this is C of E minus L of E. I've reduced it, and then we can increase the demand here by the lower bound, and I'm going to kind of compensate for that. This is going to be that. What is it? Plus 3.
It should be
Minus 3. Yes. Minus 3. Thank you. Okay, so it just means I'm kind of consuming these 3 units here kind of temporarily, then just trying to meet this bound, and then reapplying these units here. Okay, so it's a transformation that is applied locally to each edge and to the endpoints of that edge. It could be that, of course, these edges into U, the other edges, have lower bounds, and that means that I will have to probably increase this du by more than 3 if there are other edges. So the transformation has to be applied for every edge in the network. But in any case, the transformation takes polynomial time, and it brings me back to a problem of this sort, which I know how to solve. Because I can reduce this problem to regular maximum flow problem. Right, so it's all, it's just like now a chain of reductions. I go from lower bounds to circulations. From circulations, I can go to max flow, and that enables me to solve the original problem. So I can always, in every case, every practical case that we will encounter, it's possible to put reductions in series, one after the other. All right, questions? All right, so let's see. So now let me show you one example of how you can use this. I'm going to switch this off. All right, so that's where we were, and we know how to solve this problem. Let's look at one actually simple but very nice application. And so generally, flow problems are very good, or the max flow problem is a nice approach to solving things, solving problems where you have to distribute some resource. Okay, so you have to. So the obvious thing is you're just supplying, bags of potato chips to a bunch of people, but then you want to split them in some way. But you can make this much more complicated. This is a slightly more complicated example of that. Okay, so this is called survey design. Example. Okay, so here's. Here's my goal is to design a survey asking N1 consumers about N2 products. maybe let's see. So maybe I can fit it all on this page if I'm lucky. Okay, so here's the thing. I've got let's say 3 consumers. Okay, so here they are. Okay, and I guess ABC is always good. And there's some products here. So here are the products. I made these up. Okay, so here are the products. And I will put an edge between a consumer. This is not consumers like here, but it's people who buy stuff. In this case, this stuff, these products. Okay, so I'm going to put an edge between a consumer and a product if that consumer owns that product. For instance, maybe I have this, and the phone, but microwave, and this person owns all 3. All right, so that means that Carol has all of those 3 products, and Bob only has a toaster and microwave. Alice has a toaster and a phone. Okay, so that's what. So what I would like to do is ask these consumers about the products they bought. Okay, so obviously I can only ask a consumer about a product if that person owns it. Okay, so one constraint is I have to ask consumer I between, let's say, CI and CI prime questions. All right, so I'm going to ask, for instance, let's see, what do I have here? I could ask, say, for instance, I can ask Carol between 2 and 3 questions. Okay, so maybe I can write a table of that in a moment. And then I will ask between PJ and PJ prime consumers about product. Okay. Okay, so I've got some limits. I say, okay, so I need, for instance, I need to know, I have to have 3 answers with 3 people responding about the phone. I guess that would be impossible, right? Because there's only 2 people that know. Okay, but maybe I can get 2 people to ask, to answer a question about the phone. So now the question is, is it possible to design a survey that meets these constraints? Okay, so it's a feasibility problem. I need to know yes or no, is it possible to do that? And for example, here's an instance of that. Okay, so that indicates who owns what, and here's an example. We might see something like this in homework, for instance, but let's say here's Alice, Bob, and Carol, and here's CI, and here's CI prime, and I can just tell you that here Alice is going to be asked between 1 and 2 questions, and Bob between 0 and 1, and Carol between 2 and 3. And then I have the product, toaster, phone, microwave, and I have PJ, PJ prime, and here I've got 2, 2, 2, 3, and 1, 1. So it says that, for instance, for the phone, you want to ask between 2 and 3 questions. For the microwave, you want to ask exactly 1 question. The toaster, exactly 2, and these are the limits that you have for the people. So Bob can be asked at most one question, but he could be asked none. All right. So I believe, and you can correct me if I'm wrong, that in this case the answer is yes, there is a survey. Yes, go ahead.
The second table, is that the number of questions each person?
No, so this is the total number of questions asked about this product. Okay, so I'm saying I want any two people, yeah, but I will only ask a person once, right? So each person will only be asked once about a specific product he or she owns. Okay, so Alice can be asked about the toaster, the phone, maybe once for each. I don't know, Alice, yeah, can be asked two questions, but Alice can't be asked about the microwave. It can't be asked two questions about the phone. Other questions about the formulation? Okay, so once you understand the formulation, there's another extra step. Yes?
Can you even what CI, CI dash, PZ, dash?
Yeah, so this is the number of questions that you can ask each person. So Alice can be asked one or between 1 and 2 questions about a product. Okay.
How did you get those back?
Those are paid somehow. Okay, that's part of the input. Okay, so the input is this. And the question is it possible to meet? Okay, so this person does not want to be asked more than 2 questions. I'm not sure how realistic that is, but if you ever go online and you get into a survey, there's a point, there's a saturation point, how many questions you can answer about it. All right. And then sometimes you're asked to answer at least some number of questions to get to where you want. All right, other questions? All right, so the question is it feasible to do that here? I think so. I think so. So well, I mean, you could try. I think if you asked, let's say, Alice about toaster and phone, and then you got 2 questions, at the limit, and the toaster needs another person, so I can ask Bob about the toaster. So that gives me 2 questions for the toaster, and I've met my target. And, sorry, Carol for the microwave and the phone. So the phone gets 2 questions, and the microwave gets 1. Again, I think that sort of met all the requirements that were stipulated in those tables. Okay, so that's a survey. There is a survey for this input. All right, so the question is, it looks a lot like a matching problem, except that, as you can see, it's possible for me to have multiple edges into a node. So I have a bipartite network, but it's not a regular matching. All right, so here's a solution. I'll just tell you what the solution is. And then you can ask me questions if you feel like it. Okay, so what I'm going to do is the following. And this is a general transformation. So here's Alice, here's Bob, here's Carol. And here is, what is it? I have the toaster, the phone, and the microwave. Okay, so it's a bipartite graph. And I'm going to put, I guess I'm just going to keep the same edges, except I'm going to direct them like this. Okay, so I've got this, this. Okay, so here's the first step. I make, like I did for bipartite matching, I have a directed graph. And then I'm going to put a source and the same as I did before. So source gets connected to the consumers, or the consumers of the product. And here are the products. And for these nodes, I have an edge. Okay. So I'm going to I'm going to indicate that a person can be asked at most 1 question by putting a capacity of 1 on each of these edges. All right? And in fact, it's going to be a network with lower bounds as well, So I'm going to put a lower bound of 0 and an upper bound of 1. So the lower bound just says, okay, I may not ask any questions, but I can ask at most one. Okay, so all of these edges here from the consumer side to the product side have the same lower and upper bounds, 0, 1. All right? Now, for this side, I think I've got the right matrix. So what I'm going to do is I'm going to put, for all of these edges, I'm going to put a lower bound equal to the CI and an upper bound of CI prime. Okay, so for instance, this is going to be 1, comma 2, and this is going to be 0, comma 1, and this is going to be 2, comma 3. And for these edges here, I'm going to put a lower bound equal to PJ and an upper bound equal to PJ prime. And so this should be, if I copy this right, it should be 2, 2, 2, 3, and 1, 1. All right, so I've transformed this from some kind of problem where I was given really 2 matrices into a graph problem, and it's actually a circulation problem. It's not quite there yet, right? So there's this is not really properly formulated. So what do I need to do to finish this transformation? I want to find some demands, right? And I want to make sure that if there is indeed a survey, there is a circulation, and if there's circulation, there's a survey. All right, so what should I make the demands? It's kind of tricky, actually. Well, I think it's kind of tricky. Maybe you don't think it's tricky. Okay, so here's what I'm going to do. I'm going to make all the demands 0. I just want to see if I can send flow through this, and here's what I'm going to do. I'm just going to put an edge back. Okay, so this is a true circulation. I want to kind of circulate flow, and I'm going to put a lower bound of 0 and an upper bound of infinity, something very large. All right. So, if indeed there is a survey that corresponds to these constraints, then I just have to, it'll just be a matter of, well, seeing how many questions I ask for each of these people, put that as a flow here, seeing how many questions were asked of these people, and then just put the corresponding flow there, and then these will be chosen accordingly. And then whatever I send here has to match whatever is going out of S and coming into T.
In the construction between the consumers and the products,
Yeah.
your edges,
Reduces to network flow. So that was one application. Now, questions before I continue? So the demands are all 0.
Why don't you need the DS edge?
Why do I need the TS edge? Okay, so it means that first of all, in response to your first question, all of these nodes are transshipment nodes. Okay, so all I want to do is make sure that the amount of flow coming in equals the amount of flow coming out. And the way I'm trying to make sure that I'm satisfying the constraints on the number of questions asked of consumers and products is by these lower and upper bounds. Okay, so I just want to make sure that the number of questions I ask here matches how many questions are asked of each of these products. So I need to have the amount of flow coming in here equal to the amount of flow coming out. And I also want the amount of flow coming out of here to equal kind of what's coming in. So I do want the demands here to be 0. I just want them to be transshipment. Now, in response to the second question, well, what would happen if I did not have this edge? Yeah, then then I wouldn't have anywhere to put the flow that's coming into here, right? So all I'm doing is I'm just shipping it back here and sending it through. Okay, so I need that extra edge just to keep everything circulating. It's a mathematical trick to make it all work. All right, other questions? Okay, so now let's do one more thing. And this I might not finish today. Yes, go ahead.
Ultimately result in the graph that shows the ask what.
Sorry?
How does it ultimately show the graph in the ask what?
How does it ultimately show who can be asked what?
How do we extract the survey
Oh.
results?
How do you extract a survey result? Okay, so suppose you have a feasible circulation. Okay, how do you extract a survey? So from circulation to survey. How? How? Okay, so look at these edges between this side and the supply, the consumers, and the product. So what's going to happen on the flows here? What's the flow going to be on each edge? 0 or 1. Okay, so if it's a 0, I mean I'm not asking this consumer about this product. If it's a 1, that means I am asking that consumer about that product. And I am making sure that these constraints I've written here are met by setting these capacities as lower bounds appropriately. Okay, so basically I can get this, the survey, just by looking at these edges and the flow on these edges. Yes?
What does the result look like if we, if it's not feasible?
If it's not feasible, it's going to say, it's just going to say it's not feasible and you can't do it. That's all. I mean, so what's going to happen is you're going to reduce this to a flow problem. The flow problem is going to say, I can't meet these requirements. I cannot saturate all the edges out of the source or into the sink, so I'm done. Now, what is it going to look like? Well, there is no solution, so I don't know what it would look like. I guess in practice, what you would like to do is perhaps in that case, then maybe reduce some of these or relax some of these constraints and try again. But in this particular problem, if you have no answer, all you have to say is no.
So in the basically bottom those max flow problem, the flow is going to end up being 0?
No, the flow is going to be something that's not saturating the source, edges out of the source.
Oh, okay.
So what's going to happen? You go from here survey design all the way down to flows, and you get a flow problem. If in that flow you're not saturating all the edges out of the source, you're done. You say no. Yes.
What if, like, for a toaster, you have many type of toaster?
Okay, yeah, there are many type of nodes there, yeah.
And then you only want to indicate, you only ask one question for each type. Then just
Oh, I guess that was once a homework problem, I think. Oh God, yeah. Okay, so you can actually put other constraints, like so you could have like you could have a company making multiple models of toaster, and you want to have a certain number of constraints on these guys. Some of those problems can be solved as network flow problems, but for every additional constraint you put, the network gets more complex. Okay, so to some extent, the answer is you can solve several of those problems as max flow, but in general, there's probably going to be a limit. But yeah, that's a good exercise, actually. What if you have multiple, a line of products, and how do you just ask the right combination of questions? I like that problem. All right, other questions? Okay, so here's another problem. This is okay. So let's step back. So now we have we've looked at this is the kind of classical flow type of problem where you try to distribute something among various parts. Okay, so here you're trying to distribute these questions among consumers and products. So here this idea of flow kind of comes very natural, very natural. Now, I'm going to show you two examples where it's more natural to look at cuts. And let me give you the first example. I don't think I've ever done this example in this class before, but okay, so here's the problem. This is a classic problem in image analysis. It's called image segmentation. And if you look the literature on image analysis, there are many papers that deal with applications of cuts to this sort of problem. So what I'm going to look at here is the simplest, possibly the simplest way in which you can apply cuts, but there are much more sophisticated ways out there. Okay, so here's the situation. In fact, maybe I can just okay. So here's an image. Okay, like in fact, like this image, like the one you're seeing there, and so there's some stuff here, like I don't know, like this and stuff or whatever. But there's this one, and you'll pardon my drawing skills, but you know, it's kind of you do what you can. Okay, so this is a hand. Okay, this is the best I could do. All right. And there's other stuff here. And like I said, it could be like a pencil here, and this, and an eraser somewhere here. But anyway, what you're interested in is extracting this. Okay, so you want to get this guy. Extract. You know, extract this from the background. So this is so there's going to be a foreground and there's going to be a background, and you want to extract the stuff from the foreground, namely the hand, from the rest of the image. Okay. So I want to separate the foreground from the background. So you can see now that this seems almost like a natural thing for cuts, because what I want to do effectively is cut this handout from the rest of the picture. All right, so now I need a more concrete model of this, and so what I have is something like this. I have a grid, and let's just write the grid here. So here's a grid. Okay, I have a grid. And this grid is where the image is, and each of these here is a pixel. Here's a pixel. Okay, that's a pixel. So there you go. Okay, so you want to label each pixel as being in the foreground or being in the background. So I want to label as the foreground or background, Okay, so there's some measure of something, intensity or whatnot, that's going to be used for that purpose. So what I'm going to do though is I'm going to then visualize this grid as a graph. Right, so this is very naturally a graph, right? So this, the pixels correspond to vertices, and the lines that join pixels correspond to edges. Okay, so B is going to be, so I have a graph G equal to BE, vertex at B, edge at E. So B is going to be a set of pixels, and E is going to be pairs of neighboring pixels. Okay, so you can see that I have an edge here, like between this pixel and there's another one here, and I have an edge between this pixel and this pixel. All right. So I have a graph. So now what I want to do is cut away the part of the graph that corresponds to the foreground from the part that corresponds to the background. And for that, I'm going to have some numbers that are going to guide me. So I have AI, so for each, for pixel I have two numbers. AI bigger than or equal to 0 is the likelihood that I is in the foreground, so FG stands for foreground, and BI, which is also non-negative, is the likelihood that I is a background pixel. All right, so I have those two, so each of these pixels has two numbers, and then for each pair ij in E, okay, so for each pair of neighboring pixels, I have Pij, which is bigger than or equal to 0, and this is going to be the separation penalty. Okay, so it's not, I want to extract that foreground by trying to maximize sort of this likelihood, but I can't just take these A's and B's, because that would probably lead me to extracting everything as foreground. So I need this other constraint, these Pij's, which is separation penalty for pixel I and J, actually labeling one of I and J as foreground and the other as background. Okay, so I have a penalty for splitting them apart, and okay, so I don't want to split things unless I absolutely have to, and I'm pretty sure that's going to give me a high quality separation. Okay, so my goal is to find a partition A comma B of the vertex set of these pixels. Right? So that's going to split this up into foreground and background that maximizes okay, so there's two things. I have these A's for okay, so I've said, so the A part is going to stand for the foreground, and the B part is going to stand for background. So I'm going to split this into the foreground part and the background part, and I want to maximize the sum of these likelihoods that I got this separation right. Okay, so I split into foreground, background, and I want to, at the same time, keep the separation penalty low, so I don't want this to be too big. So this is going to be for all I comma j in E, for all edges, such that A intersection I comma j is equal to 1. Okay, so let's just what remains of the time. So I want to. So this part is sort of, I guess, intuitive. You just want to maximize these total likelihoods that you've got the foreground and background right, and you want to keep this separation penalty low. So I look at all the edges, and I'm just interested in those edges that go from A to B, right? So that means that the intersection of the A side with the endpoints of that edge of those edges has at most one element. Right? In fact, that's exactly one element. So one endpoint is in A, the other endpoint is in B. All right. So this says I'm just cutting away this image or this part of this foreground, maximizing the likelihood that I got the foreground and the background scores right, and kept the separation penalty low. Okay. So just cutting that out. So this looks very much like, yes?
Is the for same I, is AI plus BI equals to 1?
AI, that doesn't have to be, no. No, I don't have any constraint like that.
So one pixel can have like 80% to be foreground and 80%.
Yeah, you'd 50-50 chance. Well, yeah, I guess it could be. It could be a number. It's could be a number. It's a number. I guess you could scale it perhaps so that it's got it balances out. Not sure if that is absolutely necessary. I'm not sure. That I don't know for a fact. Okay, but I guess you could say, okay, that you could, if these were probabilities, you would probably have that they add up to 1, yes. All right. And in any case, the formulation I'm going to give you is going to still work. All right, so we're almost done, but okay, so you can see here that this looks a lot like a cut problem because I'm trying to split away one part of the vertex edge from the other part. The only kind of weird thing is that it's not just edges that I'm cutting, I'm also taking into account the cost of the vertices. Okay, so it's this part that's a little bit strange. And what I'm going to show you next time is how you can handle it. Just make it a regular cut part. Okay, no, that's not.